So last time we talked quite a bit about this equation, which describes the diode's characteristic in the forward and the reverse all the way until the sort of before the breakdown happens here. So this was the characteristic that was sort of defined by this equation. I is equal to is e to the v over vt minus 1. So this equation we talked about last time, it defines this shape, right? In this case we said that Vt is called the thermal voltage, and it's a constant that is temperature dependent, and it's equal to K times temperature divided by charge. So this is a temperature dependent constant that we found was equal to approximately 25 millivolts at room temperature. So at T is equal to 25 degrees C, we calculated Vt, which is a thermal voltage, to be 25 millivolts. So if I is greater than Is, and Is is a saturation current, so Is is the current that we find here at this node here, at this moment, this is the magnitude of the maximum saturation current, or the drift current that is in the reverse direction here. So where this is V and this is I. If I'm operating in the forward region, if I know I'm operating in the forward region, right? I can, meaning I is greater than the saturation current. The current is significantly greater than saturation current. I can sort of drop this one. Do we agree? This one was there to do what? This one was there to make I equal to minus Is in the case of V becoming 0 or less, right? If e to the 0 is 1, 1 minus 1, e to the 0 is 1, 1 minus 1 is 0, that's this point here. And if I go V negative, then this is e to the minus x. If x is big, then this goes to 0, and I'm left with I is equal to minus s in this region, right? This is what I have here. If I'm operating in the forward region, if I'm operating with this, I can then drop this minus 1. I can say that I is equal to is e to the v over vt. Yeah, that I can approximate the current with this exponential in the forward direction, which matches the concentration of the charges that we saw before being exponential. Yeah. Anyway, so if this is the case, I can also, if I take the natural log, I can take the natural log on both sides. If I divide I by is, I divide I by is equal to e to the v over vt, right? I take the natural log of both sides. I get what? I get v over vt is equal to, so v over vt, I can bring vt to the other side, so v equals vt, right? Natural log I over is, right? So these are two identical equations, right? I can also, instead of taking the natural log, I can take the log base 10. Log base 10, log base 10 of e to the x is equal to x over 2.3. We will find that useful in another, in the next page, right? So I can here I took the natural log, right? I took this equation, I had this equation, I took the natural log, I came up with another equation, right? And this is the voltage across the diode still, and this is still the thermal voltage, this is still the saturation current, and this is the current to the diode. So these are my operating characteristics, right? This is my voltage and this is the current. I can write it in this fashion, or I can write it in this fashion, or I can write, instead of taking the natural log, I can take the log base 10 on both sides, and I will end up with an equation on the next page that will be useful. Instead of natural log, log base 10 here, and I will have a 2.3 Vt here. So because of this identity, right? So instead of taking natural log, I'll do that. I'll do that on the next page. So everybody's okay with this approximation? It's just an approximation when I'm operating in the forward region. Okay? It's what? The Vt is here. Vt is here.
Isn't there an mixed by n also?
No.
So
Why? No. This is what we discussed yesterday. This was this current here from the forward and the reverse. All I'm saying is that if I'm in the forward, fine, I don't really care about this. So if I don't care about this, I can drop this -1 from this equation. If I drop this -1, I end up with this equation. This equation I can rewrite. I can take the natural log on both sides and simplify and rewrite in this fashion. Or I can take the exponential log of both sides. So if I take log base 10 of e to the x, so I bring I over is still here, equal to e to the v over vt. Instead of taking the natural log, I take the log base 10. So I will end up with log base 10 of I over is is equal to what? V over vt, v over 2.3 vt. Right? So, just several ways of doing it. So, and I will find some use for some of this stuff next. We will find that this 2.3 vt is a nice interesting number, because 2.3 vt is equal to what? Vt we said is equal to 25 millivolts at room temperature. So 2.3 vt is equal to 2.3 times 25. Calculator. Yeah, approximately 60 millivolts, right? So we will see that this is going to be interesting for us very shortly. Yeah, very interesting about 60 millivolts. So anyway, so this is what we discussed here. Vt is a certain 2.3, a certain number based on the material k. It's k times t divided by the charge. That's simplified in this fashion, and we have these two equations that I came up with right now, right? So I'll take my current equation, and now let's say I have two operating points. I'm operating this diode at a certain current I1, and I'm operating this diode at a certain current I2. You can see, right? Okay, if I'm operating this diode to these two certain currents, how does that look on the operating characteristics? Let's draw the this is my diode operating characteristic again. I'll draw the forward region now, since this is now more important for us. Right, this is voltage on the diode, right? This is diode voltage, and this is diode current. If I'm operating at I1, do you agree that I will have a certain V1 across the diode? And if I'm operating at I2, I will have a certain V2 across the diode. So these are two operating points, right? So if I make the ratio between, so I will come, it's fine. So I have this equation and I have this equation. I will write them as a ratio. If I write them as a ratio and I use the same idea of taking the natural log on both sides or taking the log base 10 on both sides, I can write this equation or this equation. Do we agree? So if that is the case, I have something interesting here. V2 minus V1, the difference in this voltage, is equal to 2.3 Vt log 2 I2 over I1. If I make I2 over I1 equals 10, for example, so current is going to change 10 times between, let's say here, this point, I1, and I2. Fine, we made it close here, but the idea is if I make current change 10 times, right? So it's like having current go from 0, or 0.1 amp, or half an amp, to 5 amp, right? 10 times the current, right? It's like going from non-conducting to conducting, or from right? It's from very low current to 10 times that, right? That's that's what you want to do with the diode, correct? So if I do that, if I make what's log of 10? Log base 10, log of 10 is 1. So which means that V2 minus V1 is equal to 2.3 Vt, right? Which tells me that if I change the current by 10 times, I only have a difference of 60 millivolts, right? That's why the 2.3 Vt was interesting, right? I only have a difference of 60 millivolt change in voltage, which basically tells me that this characteristic is, which tells me this characteristic, is like this, and I can all of this is really between a very narrow band range, and that's why I can assume this 0.7 volts that we said before. If this happens to be, if V1 or V2 happens to be 0.7 volts, if one of them happens to be 0.7 volts, then fine, it doesn't matter. The other one is 0.7 plus 30 millivolts minus 30 millivolts. I'm able to this. Then I'm just trying to prove to you that this exponential model is very close to the fixed forward voltage model, right? The fixed forward voltage model, we assumed the fixed voltage across the diode, right? Even though current changed by 10 times, this voltage didn't change much, right? So that's another justification for your, the fixed voltage model, which tells me that if I have a diode that is pushing 1 amp, or if I have a diode that is pushing through 10 amp, it's okay to model this as only the 0.7 volt fixed voltage model. It's also okay to model this as the 0.7 volts fixed voltage model that we talked about before. Right? This is the objective of this discussion here. Okay.
So diode doesn't amplify. That's what it says, right?
No, we didn't say it doesn't amplify. Here, I'm just saying that it's okay to use the 6 volt. No, on the contrary, I took I can amplify from 1 amp to 10 amp without changing the characteristics of the voltage across the diode much. That's what it says. No, I'm amplifying. I can have this thing go from 1 amp to 10 amp, and the model is still the same. Very similar, right? So I will get to this amplification shortly. Okay. So now that we've said this, we also see here from this equation that Vt is a temperature-dependent variable, right? It's a temperature-dependent variable. Fine, at room temperature 25 millivolts, right? But Vt is it's temperature-dependent, and it's equal to here K times temperature over Q. K is a material constant, and this is charge. So it's a linearly proportional to temperature. Is as well. Is is what? This is the saturation current. Remember the saturation current? Saturation current is also a temperature-dependent quality, right? So what I see here on the next page is if I'm actually going to change temperature, these diode characteristics will change with temperature. So I can use this diode as a temperature sensor, for example, right? So how do I do that? I will pass a certain current through the diode, and I look at the voltage drop across the diode, measure that all the time. So if I measure it here, I get a certain voltage, Vt2. Here I measure it here, I get Vt1. This is actual voltage across the diode, right? So it will change with temperature. So it can be used as a temperature sensor. So and this is called. So diodes are said to have a temperature coefficient, right? So temperature coefficient is typically given as a number in volts per degree Celsius. So the voltage drop, the forward voltage that we talked about across the diode, this is 0.7 volts, changes by about -2 millivolts per degree Celsius. This is called negative temperature coefficient. So you increase temperature, voltage drops by 2 millivolts every degree C. So why not use it as a temperature sensor? So there are temperature sensors based on diode characteristics. You will have a sensor. You can use some temperature sensors are based on this. Okay. We talked about the reverse bias region where I becomes equal to the negative saturation current, and we said that the saturation current is, theoretically speaking, is in the order of 10 to the minus 15 amps. So it's a really, really small value of current. But is this really all you have when you are operating the diode in reverse characteristics? When you are operating the diode in reverse, meaning you are putting a more positive voltage here versus a negative voltage here, we know that the current that's flowing, right, is the saturation current. That's from our previous discussion. But it's actually not only the saturation current, it's saturation current plus some leakage. Right? Like any, a capacitor. Capacitor has a dielectric. This dielectric will have a leakage current. If you place different charges across the dielectric, it will have leakage current flowing. It's not going to be an perfect insulator. There's no such thing as a perfect insulator. There is always a leakage current here. But is this really a big deal? Not really. We see here that, instead of 10 to the minus 15, the actual current increases a little bit to 10 to the minus 9. Right? So, but it's still very small, basically, right? So that's what this section here is referring to. Breakdown region. We discussed the Zener effect quite a bit before, so I will talk about it later in the chapter in more detail. So I'll just this is just as you hear that you can operate the diode in reverse mode, and if in reverse mode there's a region called Zener mode that is safe to operate in, and we will discuss that later in the chapter. So I will just move. It's just a quick discussion here. Then. Now, formalizing our discussion of this diode modeling, right? So we talked about the exponential model of the diode. We also talked about the forward voltage model of the diode, and we talked about, ideal voltage model of the diode, just a pure switch without any forward voltage drop across the diode, right? So we had these three models. So which one do you use, right? So this, here we will discuss and we will do some examples on numbers and see the difference between the various models, as well as look at diode operation as an amplifier. So we know where this comes from. So if I'm operating the diode at a specific value of current, this is our equation where we drop the -1, because we said that we're operating only in the forward, right? Only in the forward characteristic. So we drop the -1 from the previous equation of current. And now I want to put this diode in a circuit here. And this, in this circuit, I have a certain power supply, VDD, and I put a resistor, and I have a diode. This is the most positive voltage in the circuit. This is the most negative voltage in the circuit, which means the voltage on the cathode side is negative versus the anode side, which means that the diode can conduct. Correct? So this diode can conduct in this circuit. So what is VD, right? And what is ID? Right? I don't know. I'm not sure where this diode is going to operate at, right? I have my forward model here. I want to know what V will be and what I will be if I put a certain value of resistor, right? That's the objective of this discussion. So I have this equation from the physics that we discussed. I also have this equation from the circuit, right? What is this equation telling me? It's telling me that, we know that this diode is modeled as what? In forward mode, I will model it as a power supply, a DC source, opposing current flow, right? Current will flow this way into the diode. The forward drop is a voltage that opposes current flow, right? Remember we said that I have to be able to increase voltage beyond the barrier voltage to allow diffusion to happen in the diode. This means that I'm modeling this diode as a voltage source in opposing current flow, right? So that's what this means. So that means I have a circuit that looks like this. Right, so this is VDD, and this is VD, and this is ID, and this is the resistor R. So how do you find the current ID flowing in this circuit? It's VDD minus VD, this voltage, minus this voltage, right? Divided by the resistance. Correct? No. 4.6 is what we talked about, 5 minutes ago. For yesterday, we talked about the forward characteristic of the diode. It was IS e to the V diode, V over VT, -1. We said that if I'm only operating in the forward characteristic, what this -1 is giving me is that at if this is 0, e to the minus x, meaning the voltage is negative, then I get I is equal to minus IS. That's what this -1 was buying me, right? This became 0, and this minus became outside. But if I'm operating only in the forward mode, then I don't care about this -1. I don't have a negative voltage anymore, so I just drop this. So I have I is equal to IS, e to the V diode over VT, which is the thermal voltage. It's a constant at a specific temperature, and that's it. That's one equation. That's modeling my characteristic. But where am I operating on this characteristic now? Is my problem, right? I put this in a circuit now. Where am I on this characteristic? What V diode, and what I do I have? I diode. Right? What V diode and what I diode do I have? Right? That's the problem I have now. Right? So these are two equations. And this is not linear. Right? The exponential function is not a linear function. Right? So these are two equations and two unknowns. Right? How do you solve two equations and two unknowns that are nonlinear? We don't know how to solve except with numerical methods. So you either iterative methods, or you do it graphically. These are two ways to solve nonlinear equations. So there's an example of how to do it graphically, and then there's an example of how to do it iteratively. And let's look at how to do it graphically first, because it helps us understand what's happening here. So we have I will rewrite the equations here for convenience. So we have one equation that says what? ID is equal to IS e to the VD over VT. And the other equation, ID is equal to VDD minus VD over R. These are my two equations. My unknowns are ID and VD. ID and VD are my unknowns. R is my circuit, VDD is my power supply, VT is a thermal voltage equal to 25 millivolts at room temperature. Right, so my unknown IS is the saturation current of a specific device. Right, these are all givens. Right, so how do I solve this graphically? Right, I can plot this and plot this. So this is plotted as this exponential function. Right, I don't know where I'm operating yet. Right, but I can plot this for various values of ID and for various values of VD. Right, so I start with put VD equals 0. And then calculate ID. VD equals 0, calculate VD equals 1, 2, 3, 4, all the way until a high value, some value. And I will plot this exponential, right? If I just keep substituting the values of VD and plot ID. Correct? And the same thing I can do with this. I can also put VD, start with VD equals 0 and calculate ID. VD equals 0, and this is a straight line. So if I put VD equals 0, this is VDD over R, that's this point here. If I put VDD equals VDD, VD equals VDD, so at VD equals VDD, I end up here, right? This is 0 on top, so I end up with here. So this is a straight line with a slope of, in this case, 1 over R, minus 1 over R, and this is this exponential function. These two will intersect at a certain point called my quiescent point or operating point. Quiescent. I don't know if this is the best way. I'll show you the spelling here. I believe this is how you pronounce it. Yeah. Quiescent point or operating point. Operating point is easier. So this is my operating point for the diode. This is my DC operating point for the diode. Do we agree? It's not changing. It's a fixed value for the circuit that I have, which gave me this equation. Do we agree? Okay. So that's the graphical way of solving this. And as I said, this is called the load line, and this point here is called the operating point, and they call it quiescent point in a section next. Okay, so that's one way of finding your operating point given a circuit, right? The other way of finding your operating point, again, it's DC operating point. Why is it DC operating point?
What is the importance of that operating point again?
The importance of that is gonna show, because again, you have a diode in a circuit.
Mm-hmm.
How much drop do you have across the diode? Let's say you want to create a voltage regulator. You want to create a voltage regulator that will put, and hook maybe a certain load across that voltage regulator, right? So let's say you have a power supply here, VDD, and you have a resistor here, and you have a diode here, and you want a certain voltage across here to be able to put a certain load, certain load here. You want to make sure that this voltage is a specific value, right? To ensure that, you have to know that what is the specific value of VD across, and what value of resistor do I put here, right? So let's say you want 0.7, so you go here, and this is 0.7 volts. That means you have to operate this circuit at a certain current ID. Then you will be able to, by knowledge of ID
You can find
and your power supply, you can find R. Right? So that's one way of applying this. The other way of applying this is going to be clear next. Okay, when we try to see when we operate this diode as an amplifier mode, and we will see why this DC operating point becomes important. So anyway, so graphically we solve. Numerically, you can solve very similar ways. So you have a circuit, and that we had this similar source, resistor, and diode type circuit. VDD was 5 volts. The resistor was 1 kilo ohm, right? And they tell you here, again, iterative methods, if you've taken any numerical analysis course, is something that you always have to guess your first answer. And if you take 459, the power systems course, we spend a good amount of time on iterative methods of solving power systems. But all iterative methods require you to always give a good guess initially. And if your guess initially is garbage, then you will get garbage, because you will have to converge. Sorry, go ahead. You guess based on your best judgment. But best judgment is engineering sense. So you know that based on our discussion, that the voltage across the diode, does it change much when the diode is conducting?
No.
No. So what is a good voltage to use?
0.7.
Exactly. Right? And you go to your characteristic of the diode, 0.7, you will typically find a current, let's say ID of 1 milliamp. For this specific diode, they assumed, okay, take diode current as 1 milliamp at 0.7 volts. And then you will iterate. Okay, let's iterate and see what happens here. So we put 0.7 in our equation, VDD minus VD over R. What do we get as diode current? 4.3 milliamp. And this is the output of the first iteration, right? So if I have, which means that my operating point is 0.7, and my current is not 1 milliamp, it's 4.3 milliamp. You see what we got a new, we assumed current is 1 milliamp, voltage is 0.7. We found that, okay, I will substitute in the equation of the circuit, and no, I don't get 1 milliamp, I get 4.3 milliamp, right? So now my current is 4.3, and my voltage is still 0.7, right?
So
But this is after the first iteration. Let's iterate again.
So you check the resistance in order to make
No, the resistor is fixed.
it's fixed.
We don't know ID, we don't know our operating point. We want our operating point VD and ID. I will guess, okay, VD is equal to something and ID is equal to something. And then substitute with this guess and see what I get from the equation. So I got from the equation ID is equal to 4.3 milliamp. Is this right or wrong? I don't know yet. If I go to the next iteration, numerical methods are typically such that if you go to the next iteration and your values are close, then you've converged. That means you're around the proper number. If your values are not converging or diverging, then you are not really finding the proper value, which means that your initial guess was wrong. Okay, this is, numerical methods. I will not be able to elaborate too much on numerical methods technique. We do that in 459 for a certain amount of time. Anyway, so what other equation can I use to plug in these numbers? So remember that the equation of the difference in voltage across the diode. This is actually the reason why we said that the diode voltage model, forward voltage model of 0.7 volt is okay. So we derived this equation initially. So this is another equation that I can utilize, because now I would like to, okay, so I calculated, you have an initial guess for voltage and current. You calculated after one iteration the value of current. You also need to do the calculation of voltage after one iteration. So the other equation that we can utilize for that is V2 minus V1 is equal to 2.3 Vt log I2 over I1. We know that V1 is 0.7 volts. So, and I want V2, so the voltage at my next iteration in this case. And I know that I1 is 4.3 milliamps, and I want my new iteration for current. So they substitute that. So they substituted V1 is 0.7 volts. I1 is, I1 is 1 milliamp. That's the initial guess, because now I want to calculate 2.
And I2 is the calculated.
Yeah, I2 is the one we calculated after the first iteration. I calculated a certain current. I want to calculate a voltage after the first iteration, which is V2, right? I have V initial, which is 0.7, which is V1. And I calculated I1, which was 4.3. And then, which was, so I was given I1, which was 1 milliamp. I calculated I2 after the first iteration, which was 4.3 milliamps. And then we substituted in this equation. After I substitute, so I substitute here with 0.7 volts for V1, and then I1 is 1 milliamp, I2 is 4.3 milliamp. I get V2 of 0.738 volts. Okay? Now I take my 0.738 volts and I can iterate again and find. Yeah, always exactly. You continue. Yeah, you assume you have an initial guess. Numerical methods, you always have an initial guess for your parameters, and then you plug them. And you look at the equations that define your system, and then you plug and find a current. And you plug and find the voltage, and then you plug again and find a current, using not the first 0.7 value now volt for voltage. No, you can use 0.738 now, right? Instead of 0.7, which was my initial guess, I can use 0.738, which was my new guess from that came out of my iteration, my first iteration. So 5 minus 0.738 divided by 1 is 4.262 milliamps. It's very close to the 4.3 milliamps.
So that's already a good point.
So it means that I'm converging. I can continue and find the exact. So I can continue and find this exact point, right? But I'm close enough to it, right? That's what I'm saying. You're close enough to it because you got a voltage of 0.738. You initially had 0.7. You got a current for 4.262 milliamp. You initially estimated at 4.3. Fine. So use your latest guess, which is ID is 4.262 milliamps and VD is 0.738. So this operating point is ID is 4.262 milliamp and VD is 0.738 volts. Okay? Graphically or numerically. That's this example. You can continue. You will probably tune it a little bit. You have V2. You can take this now. You can take this voltage and then plug it back again into the current this equation. In VDD minus instead of
You already did it. So you'll go back to the V2 minus V1.
You will go back to the V2 minus V1,
And
where
then you'll use the
V2 will be
4.62.
the one you want to calculate,
But then, sir,
and V1 will be the 0.738.
but then I1 will change now.
Sure.
I1 will be 4.3.
Exactly.
And I2 will be
0.262 milliamps. Exactly.
And then
Right.
you'll come closer to the point until you reach it.
Exactly. But do I really care? I don't mean fine.
But I think this needs limits.
But that's why in numerical methods you always have a convergence criteria. Convergence criteria means you subtract the last two values, your newest calculation and the previous calculation. Subtract them. If it's smaller than a certain value that you specify as an engineer, then it's okay, right? So that's yeah. It's 0.738 versus 0.7. It's all close. If you do it again, you will get 0.738, maybe 381, or 382, or 39, right? So it's fine to stop. I mean, that's why all they're saying is that we found it. We can stop. I mean, and actually the nice thing about this is what's happening here. What did I use here? I used 0.7, right? 0.7 is what we always said. Okay, the approximate forward voltage model is this. Is that my forward voltage looks like this, right? And this number is 0.7. So I used that initially, and I got something as close as possible to. Here I didn't, here what did I do? After that, I applied this is coming from my exponential current equation, right? So if you use your exponential current equation, you get something close to what your fixed forward voltage equation is giving you, right? That tells you what? That tells you that your fixed forward voltage model is enough. Is a good enough model here. Right, so that's what the moral of this story is. Yeah. So we were able to calculate the operating point, but the biggest moral of the story is what they talk about here in this section. Yes, ma'am.
Do you have a method where we calculate it accurately, rather than using graphs?
No. Nonlinear equations can either be solved graphically or solved using iteration. There's no exact solution. Even in power systems, there's no exact solution.
So basically, sir, anything with 1 in this equation, the V2 is equal to V1 plus anything with 1, that's the initial guess.
Yes,
And anything with 2 is the
current value, the new value. Current value,
and
new
then
value.
You go
Current
to the
value,
second equation, which is the finding ID.
Yeah.
And you use the second guess.
Sure.
And then what you get is the initial guess for the second equation. If you're gonna
Exactly. If you're gonna apply another iteration.
Yeah.
Sure.
So every time you find ID, you're finding I1.
Exactly. In this equation, in this sense. Again, if we cover numerical methods again in power systems, we cover that in more detail in numerical methods. So
It's good
so we
to know.
actually call we say that this is V at iteration 0, V at iteration 1, V at iteration 2. We formalize it a bit more. Here it's not, informal. The objective of this discussion is summarized in this next section. In this next section, they tell you, okay, if I had just used my forward voltage model of 0.7, I was getting something close enough even from the first calculation. And I did not need iteration. That's the objective of this discussion. And and it's fine because the 0.7 didn't change much, and even after iteration, my 4.3 changed to 4.262. Did not change much, right? So that the objective is the objective is to justify the constant voltage drop model of 0.7 volts. All of this discussion is to justify that. Okay, so it just tells you that. Okay, then all of this, this is, why don't you just use this? It's much easier. That's what they're saying.
That's why I said in the beginning, the first time we talked about diodes, we said that they have a range between 0.6 to 0.1.
Yeah.
That's why we said that.
Yes, and then we proved that even if current changes significantly with this exponential function,
It was,
that the voltage will only change by 60 millivolts. Maximum it will change by 60 millivolts, right? So this all justifies the simple forward voltage drop model out of the diode. Okay. And if you utilize the ideal diode model, meaning the voltage drop is 0, it's 5 minus 0 over 1. You get 5 milliamp. This is quite different from 4.3 milliamp. 4.3 was so close to the 4.262, versus this is 5 milliamp. So considerably different, about 15% difference, right? So they're just saying all of this is justifying still the forward diode voltage drop model, right? All of this is still helping you.
Basically, the forward diode model is the non-ideal.
Is a nice model to use for quick analysis. That's all it's saying.
That's the non-ideal.
Yeah, I mean, ideal is the exponential model. The real model, sorry, not ideal. The real model is the exponential model. The ideal is 0 forward drop across it. As soon as you have positive voltage on the anode versus cathode, the diode conducts.
So
This is not true. You have to have voltage that overcomes the barrier voltage, which is around 0.7
so
volts.
it's either open circuit or closed circuit for
Ideal, yes, exactly. And that we found is going to give you a result that is 20% off, which is not good. You have a better way to do it with a simple modification, right? So that's this. Now, this is this is the next next main topic is, okay, how do I use this diode as an amplifier, or can I use this diode as an amplifier? So the previous discussion, we came up with what? We came up with this operating point, right? In the previous discussion, we came up with this operating point. And we know how to do that now, right? So what if now I change my circuit? I had a circuit that looked like this, right? I had a circuit that looked like this, and this was my diode, and this is the voltage that I was measuring across the diode, VD, right? And this was my power supply voltage, this was my resistor, this was my ID, right? From this circuit we found this point, right? What if I change my circuit to this? This is still VDD, and this is my diode voltage, VD, this is R, and this is, what do they call it? V small d. It's difficult to draw. This is like a DC voltage, capital V is a DC voltage, and this is like an AC voltage. Here it's that this is this triangular voltage, right? So I've now added a triangular voltage here. This is my triangular voltage. So I've added a triangular voltage in series with my DC voltage, right? I will still have current flowing in here, but this current is no longer this capital ID that I had before, right? So no. Good point. I mean, we will see what we want to do next. So in linear circuits, how do you solve this in linear circuits? How would you solve a circuit with two sources in linear circuits? How do I find the current I flowing in here if this circuit is linear, assuming I tell you this, I cover this diode. You know the diode is nonlinear, right? It's on and off, exponential characteristic, it's nonlinear. But let's say I cover the diode, I put a box around it here, and I tell you this is a linear circuit. How would you solve a linear circuit with two sources? Add them, but how do you add them? You add them, one is AC, one is DC. How would you solve it? KVL, fine. Let's say, again, one is AC and one is DC, right? So if you have a capacitors and inductors in a linear circuit, and you want to solve that linear circuit for an AC and a DC source, what would you do? Trying to make it easier. Because capacitors and inductors, okay, for a DC, capacitors open circuit, inductors short circuit, right? So you will solve your circuit for DC. And then you will solve it for AC, and then you add them. Like we did for the op amps, we use superposition. Superposition is a super tool, right? That's why it's called superposition, because it's a super tool. So anyway, you would solve it using superposition, right? So one way to do this is to approach it using superposition. But I cannot apply superposition if this is a non-linear circuit. I cannot apply superposition. But if somehow this diode is behaving like a linear device, then I can. How can you know that? It's if this voltage is small with respect to Vt. So if the voltage V of this V small d is over Vt is less than 1. Vt we said is what? No. 25 millivolts. At room temperature we say is 25 millivolts. Right? So, something over, so, this is 25, something less than 1. So, its maximum value should be 1. 5 millivolts. 5 over 25 is, less than 1/4. 1/5, so 20%. So it's 0.2. 0.2 is less than 1, considerably less than 1. So if Vd has a magnitude that is considerably in the ballpark of 5 millivolts, then what will happen? What will happen is the majority of, or the biggest determinant of where the circuit is operating will be decided by your, again, remember this is 5 millivolts, which is 0.05 volts, right? 0.05 or 0.005? So 0.005, right? 1, 2, 3, 5 millivolts, so 0.005 volts, right? If I am gonna put a source of 0.005 volts, is this diode gonna forward bias? What is the minimum VDD required to push current through the circuit? Remember, I have to overcome my forward voltage. This diode is modeled as what? This diode here is modeled as a 0.7 volt power supply in the reverse direction, ideally, right? So, which means that if I want to push any current through this circuit to oppose this forward voltage, this VDD has to at least be 0.7 volts. How does 0.7 volts compare to 0.005 volts? No comparison, right? So, if this is satisfied, what's happening? What's happening is that, and you are operating in forward mode. If this is satisfied, and somehow you're operating in forward mode, meaning this power supply voltage is considerably larger than this small VD, then your circuit operating point is really defined by your DC operating characteristics, your VD and ID that you initially found from the previous exercise, either graphically or using iteration. So, how would you find those? Only consider VDD and the resistor and the diode, forward drop of 0.7 volts. Forget about this V for a while. Right? If you do that, you can find this, right? After you have found this, you know that your signal is small, 0.005 volts, much smaller than your 60 millivolt range or much smaller than 25 millivolts, right? So if your signal is, like it looks like a triangular waveform here, your voltage will cause, your additional voltage here will cause an additional current to flow. Right? This additional current to flow will be determined by the operating, so you have voltage here, it will cause a corresponding current up here, right? If you have a voltage here, it will cause a corresponding current down here. Because, no, the VD, the small VD. Now VD brought you to this operating point that we figured out how to calculate iteratively and graphically. Now the V small d is doing what? Small changes around the operating point. Actually, it's called the DC operating point, or the DC bias point. Remember the bias currents into the op-amp? So this is exactly there. This is exactly something similar to that. We will talk about, the transistors will have something similar. But what did I require? Here, what is the diode doing actually? If I'm making a small change in the input voltage, what is it doing to the current? Is this change equal to this change? It looks considerably larger, right? So I'm actually amplifying it. So the diode is able to. So initially I had, this is my operating point, ID. Now I put a small signal in the voltage. I amplified the current. So this is my original current. I amplified the current with respect to my original using a small voltage, right? It's like the sensor that we had in the amplifiers. So sensor is giving me this small voltage waveform. I want to operate this diode as an amplifier, current amplifier. My current was this value from the DC operating point or the DC bias point, right? And I put a small voltage signal and I want to amplify it at the output. So I amplified it at the output based on what? Based on the diode characteristic, right? This point here comes from where? From the fact that you made a small change in voltage. This small change in voltage corresponded to a change in current that is a little bigger, right?
Does it have to be DC?
No, I mean if you increase, but then if you just add DC, then you're just changing your DC operating point.
Because they would be added up.
Yeah, it's just DC operating point. You're not operating it as an amplifier anymore, right? So, but if you want to amplify a signal coming from a sensor, for example, that's you can add that sensor here. That sensor is providing a small AC signal. You want to amplify that current due to that signal. Yeah, that's one way to do it. Yeah. So and it's because of the characteristic of the diode, right? And if you zoom in close, right? If this signal is small enough, I'm operating only in this region, right? This region looks like a straight line. Straight line with a slope of delta I, right? Delta Y over delta V. Delta I over delta V, right? The delta Y, to find the slope of a straight line, how do you find? It's delta Y over delta X. Delta Y happens to be the change in diode current. And delta X happens to be the change in diode voltage. So it's delta I over delta V. What Ohm's law says, V equals IR, right? So V over I equal to R. How about I over V? Equals 1 over R, right? So I will call this the slope of this straight line that's that's tangential to the operating point. I'll call this slope 1 over RD. Right?
D is the resistor in the circuit?
RD is a model of the diode. No, why is it the resistor of the circuit? The resistance of the circuit helped us find the DC operating point. Now I want to see what is the effect of this small signal. Right? So for me to find the effect of the small signal, I added the small signal to the DC operating point around here, and because it's much less than VT, I can do that. And when I did that, I was able to amplify the current from my original. Changed basically. I was amplified. So my original current was this ID. I was able to amplify my my input signal to a different value based on this input signal that I have.
If the condition here is not satisfied.
No. If the condition is not satisfied, you cannot operate in this fashion.
Then what would I do?
So, no, you cannot. You cannot operate in this fashion. So the benefit here, this is, for example, useful when you're designing a voltage regulator. It's really not useful for amplifying signals. But when you're designing a voltage regulator, you have a power supply. This power supply, we talked about flicker of the lights before, right? All power supplies have a line regulation limit, meaning they operate between a certain value. There's no such thing as a 10 volt power supply. You will measure it 10 volt plus minus something, right? This plus minus something is ripple, right? So if you're designing a voltage regulator, using a diode, and the ripple is within a certain amount, then you can use a diode as a voltage regulator. That comes to your question, Joel, some time back. At some point, you cannot use the diode as a voltage regulator anymore because your ripple becomes considerably larger than 25 millivolts per diode. If the ripple per diode is greater than 25 if the ripple per diode is considerably larger than 5 millivolts, or comparable to 25 millivolts, I cannot use this stuff anymore. I cannot use the diode as a voltage regulator, and we have example about that. This is the application of this.
It is like basic one.
Capital VDD is a supply volt. No, small VD is yes. Again, this ripple is fixed value. No, it doesn't need to be fixed value. It's a ripple on top of your DC. Think of it as a ripple on top of your DC, and you want to create a voltage regulator, right? The only reason that you will only be able to apply this superposition and figure out what value you will get at VD if this signal is smaller, right? Do we agree that we can apply superposition if only for a linear circuit? That was the justification. And I'm trying to see my goal is to see what my output voltage is. I want to see what my output voltage is. Now I have a supply that is DC with some ripple. But this ripple is much smaller than VT, or VD over VT is smaller than 1. If that is the case, since that is the case, what can I do? I can apply superposition, meaning I can deal with this circuit alone here, and then I can construct another circuit with only this ripple and this resistor and this diode. And I assume that the diode will be forward biased. But what do I put instead of the diode? Okay, that's a good, maybe that's what I missed. In this case, what did I put instead of the diode? What's the model that I used? This forward drop model, right? I put a voltage source here, and I was subtracted VDD minus 0.7, right? And I calculated the curve. That's what we did in the example, correct? But now, what do you do with this? Here, if I'm going to use superposition, that means what? That means I'm gonna now come up with a circuit to represent this effect of this ripple on the diode, right? So now when superposition, what do? You short one source and you look at the effect of the other source on the circuit. So here I shorted this source. I placed a short circuit around this source. And I looked at the effect of the other source VDD on the circuit. How did I study this effect? I removed the diode and put a forward voltage of 0.7 volt, and I calculated the current, right? That we did in the example, and that gives us this point. Okay, we're good. Now, superposition means I have to take care of the other source, so which means I have to short this one and keep this one in the circuit. Okay, what do I put instead of the diode? No, I cannot put the reverse this reverse supply is 0.7 volts. This thing is 5 millivolts max. So what do I do? Because I want to use superposition. For superposition, it has to be linear. Linear means this cannot be very large. We limited it actually to 5 millivolts. So what do? I have to find a way. This is my triangular waveform. I have to find something to put instead of this diode. What do I put instead of this diode? What do I put instead of this diode? Let's look at the equation and we'll come back to it, okay? The equation will show us that what I can put here. Okay, let's look at the equations. We'll come back to this idea. Okay, but we need to look at the equations. It will be easier when we look at the equations following each other. So this is the case where I have my DC operating point by itself. Okay, this is only my DC operating point. Right? We said that I will now change my voltage that I'm applying. So the voltage when the signal VD of t is applied, total instantaneous diode voltage will be given by, so the voltage across the diode is now my DC voltage plus the small signal, right? So I will, instead of this VD being the DC that I had across the diode, I will do what? My diode, what I'm putting across the diode now is a DC voltage plus a small AC signal, right? I substitute that in this equation for current, right? Instead of this VD, this is my DC case. My DC case, I had a certain voltage across the diode, right? My AC case, this is what? This is voltage that I'm adding. This is voltage that is being added to the source, right? And both of these are placed across the diode VD. I'm placing both of these across the diode voltage, across the diode, correct? So let's see what the effect is on the equation. So if I only have my DC voltage, if I only have VD, V capital D, what is V small d? V small d is V capital D. What is the current flowing? The current is defined by my exponential equation. So the current is Is, e to the capital VD over Vt. We're okay with that? Okay. If I now add my small voltage to my DC voltage, then I have a voltage here, V small capital D of T. That is placed across my diode. So now, this is placed across my diode. I want to plug it into the exponential equation for current to figure out what my current is for the diode. So I do that. So I take that, I replace V capital D with V capital D plus small v small d. I replace that into the equation for diode current. So diode current is now defined by this equation. We agree? In the forward mode. If that is the case, okay, then I can, how about, from exponential, from the identities of the exponential function, I can, if I'm adding two terms in the exponentials, into the exponentials power here, I can multiply, I can split them up, right? So I can write Is e to the capital Vd over T plus multiplied by e to the small Vd over Vt, right? If I do that, what is this?
This is just our
Exactly. This is the case with only a DC applied to the diode.
The ID which we
Yeah, the original. This is the DC operating point, right? That's the DC operating point. You agree?
because it's a DC.
Yeah, it's only the capital VD and over VT. It's only the effect of the DC operating point. So that's only the effect of the DC operating point, and this will give me an additional effect. So I can rewrite this, the current in the diode, as this ID. I will call it. This is the current from the DC operating point multiplied by e to the Vd over T, right? If Vd over T is smaller than 1, which is what we said has to be the case. The case has to be Vd over T has to be smaller than 1, otherwise I cannot use this stuff, right? Because I can use superposition only if it's linear, and for it to be linear, this has to be the case, right? Then I can use a series expansion of the exponential. So the exponential can be expanded in terms of a series, and if you take only the first two terms of the series, I can rewrite this equation
X to the M over N factor.
in terms of, I can rewrite it in this format. Let me rewrite this format as what? ID is equal to capital ID plus ID over Vt times Vd, right? What does this equation say? That the current flowing through my diode due to both sources is equal to what? Is equal to my DC operating point current, right? That's my DC operating point current, plus a gain multiplied by this voltage that I've placed in. So basically, I'm amplifying this voltage with a number. Is it clear what I did? Yes? So
This scaling.
V equals IR, correct? This is I over V. So I over V is equal to 1 over R, right? So I will this is I over V, right? So I will replace this I over V with a 1 over R. We're okay with that? And I will call this R, and this R is what? Is the gain, or this I over V is the gain that I have to multiply my input signal by, my input small signal by, and see and the corresponding effect on the output.
So we put a resistor.
Exactly. So I will put a resistor in the model, and that resistor will have a value of I over V, which is the slope of the exponential at the DC operating point. Right? So that was the moral of this story, and this RD is here. So R is 1 over R is I over V, R is V over T, VT over ID. So, and this is this was the moral of the story. So this is my thermal voltage, and this is my DC operating point current, right? So I will replace, so it's called the diode small signal conductance, or diode small signal resistance. The R is the small signal resistance, 1 over R is the small signal conductance. So the slope is actually the 1 over R. So it's a small signal conductance. The inverse of the slope is the small signal resistance. It's also called the incremental resistance. So
So it's the signal multiplied by the slope.
exactly, signal multiplied by the slope. So that's what we have here. So we will replace the diode in that new circuit. We started late, so
Okay.
we started a few minutes. Yeah. So we will replace the diode. So remember, now we have two circuits, right? We have my DC operating circuit and my AC small signal circuit, right? So now you're given this case. Now you have to find, and then you're told the circuit, consider the circuit, blah, 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 resistor is given, 10 kilo ohms, and the power supply has a DC value of 10 volts, right? This is 10 volts, but it also has a 60 hertz sinusoid of 1 volt peak amplitude, okay? That is not your small v, that is the ripple on the power supply, okay? It's gonna cause a certain ripple on your voltage. You have to make sure that that ripple on the voltage is less than 5 millivolt for this to be valid.
So it's not given this one.
No, it's not given yet. It's not given yet, right? But that's what we have to do. So how do we go about this? So they're asking you to do what? They're asking you. So they're telling you this is basically an imperfection of the power supply. It is known that the power supply ripple, it's known as the power supply ripple. Calculate both the DC voltage of the diode and the amplitude of the sine wave appearing across it. So what do I want? This DC voltage ripple in the power supply is going to cause ripple across my diode. Right? Remember, my goal is to use the diode as a regulator, for example. Right? So if I'm doing that, I want to look at the voltage ripple across the diode due to what? Due to voltage ripples in the power supply, for example. So now you have to solve your circuit in two ways. First, you have to find the DC operating point. How do you find the DC operating point? You have to draw the DC operating point circuit, right? The DC operating point circuit will look like what? You have a 10 volt here, power supply. This is your 10 volt. You have a resistor, R, and you have your diode forward drop model, 0.7. This you will find your ID, and VD you will assume is 0.7.
So the first thing we find is
I was thinking,
Exactly. The first thing you find is ID.
I was 10 kilo ohm. We have 10 minus 0.7.
Sure, that's.
Over resistance. You will get.
But then what should we do? We want to find. We have to find then we find the small signal analysis, right? So first we did the large signal to find VD and ID. VD is 0.7. Assume that the diode voltage drop 0.7 at 1 milliamp. So you can iterate if you want to find the more precise value of VD and ID, or you found ID from this simple 10 volt minus 0.7 divided by R, which we said is going to give us a good enough number, right? So let's stop here, and then now you do this. No, stop here from some DC analysis point of view, and then 2 minutes I'll stop, and then we have to do the AC analysis. The AC analysis. So what do we do? Remember, we said that I have to replace my diode. So this is still my DC source, but in this case it's it's my small signal source, which is Vs, right? In this case it's what? It's a sinusoid with a 1 volt peak. This is 1 volt peak, right? And then I still have my resistor, and I replaced my diode with my RD.
If we don't know the
You don't know Vs? No, you know Vs. It's 60 hertz with a 1 volt peak.
And you know,
don't we
and the small r is equal to what? Small r is equal to Vt, which is 25 millivolt, divided by your ID current, which is your DC operating point current. So you know small RD as well. So now you have a simple circuit, and you have everything that you need to calculate VD. And let's look at their solution quickly. So they did this 10 minus 0.7 divided by 10 kilo ohms is the resistance. You have 0.93 milliamp ID. How do you calculate VT? It's 25 millivolts over 0.93 milliamps, right? You get a small certain value of resistor. Then
This VD represents
That's what she's gonna call.
VT is the thermal voltage. VD where? اللي تحت where? Now this VD is the voltage on the diode, right? Due to what? Due to the VS ripple, which was given, right? The VS ripple is a sine wave with a 1 volt peak to peak. So they're asking you what is the peak value of the diode voltage ripple, right? Remember the diode voltage will be 0.7 plus some ripple minus some ripple, right? What's the peak value of that ripple? It's equal to the peak value of the input sine wave and then the voltage divider rule. This is less than 5 millivolts, right?
A lot.
A lot less than not a lot. It's half of it. It's less, but it's less than 5 millivolt, which means I can use this linear analysis simplification. If this is greater than 5 millivolts, you cannot,
Yeah, exactly.
right? But because it's less than 5 millivolts, yeah, exactly. VT, V of the diode, the ripple voltage on the diode, over VT has to be less than 1. So we said that the voltage ripple across the diode should be a maximum of 5 millivolts for you to be able to use this analysis and treat this as a linear circuit. Here it turned out to be the case, so we're fine. Okay? So
Otherwise, we say we can't.
otherwise we say we cannot solve it this way.
Okay.
We cannot solve it this
Obviously,
way.
that's
So we cannot use this as a voltage regulator. So otherwise this will give you a much bigger ripple. And hence you cannot use it as a voltage regulator anymore.
we can just say it's the
Right.
diameter.
I'm going to say what?
Because before it said it's either converters or diverters.
No, not divergence. I mean, you don't have a solution. You cannot use it as a voltage ripple. You cannot use, because if you want to design a voltage regulator, somebody wants to put something that is going to be supplied by your voltage regulator. If I'm going to put something, a critical piece of equipment supplied by your voltage regulator, I have to know what this voltage regulator is going to give me. Okay, it's going to give me 0.7 plus minus a certain range so that I can design my equipment for that. Otherwise, my equipment will burn. Right? So you need to make sure that you satisfy the requirements of the person that's going to plug a load onto your voltage regulator. Hmm? The homework is due today, right? Or the homework for the diode? I think it has to be quiz on Sunday. It's not possible. Yeah.
Wait, what was due today?
No, it's not due to. I mean, we didn't finish the material. No, it's not due.